What is the flow problem? What's the input of the flow problem and what's the output? What do you expect from it? Anyone? Should I point fingers? Bolo? Flow, network flow problem. Does anyone remember? Or do you remember? What was the flow problem? Go ahead.
नेटवर्क ग्राफ है उसमें आपको बेसिकली द मिनिमम लाइक द बॉटलनेक बेस्ड ऑन द ओवरऑल फ्लो मतलब हर कट पे
Okay.
और लाइक उसके जो आपका सोर्स है और आपके जो टारगेट है.
So let's थोड़ा सा इसको formalize करते हैं. So your input is a graph, and graph is directed or undirected. Directed. There are weights on the edges. Okay, weights negative है, non-negative है, कुछ भी हो सकते हैं. Positive है. Okay, cool. And you have a start node and you have a destination node. Okay, cool. That's the input. And what's the output?
The maximum possible flow that can be.
Okay, the maximum possible flow that you can push from the start to the destination. अब यहाँ पे you use the term flow. उसको आपको define करना पड़ेगा. What is the flow? Anyone? What's the flow? So far so good. So far, I mean, that's one of the requirements. One of the expectations I have from you guys to be able to formally describe an algorithmic problem, right? NP-Completeness में भी यही है जो हम आज discuss करने जा रहे हैं. The first basic thing is that you should be able to formally define what the problem is. And formally define, what I mean is that you should be able to tell me what's the input of the problem and what is expected as the output of a problem, right? Cool. And you have pretty much done it. उसके अंदर you used the term flow and now you have to define what flow is.
There are two invariants that no flow can be greater than the capacity of the
Okay,
and
okay.
no node can store the like any flow.
Okay.
Conservation.
Right, okay. So the flow is defined in terms of two constraints. And so flow is basically a number. It represents the amount of things that you can push from start to destination with two constraints. One of the constraints is that none of the nodes can store any flow. None of the nodes except for the start and the destination nodes store any flow. Okay, so the inflow to a node must be equal to the outflow at the node. And the second constraint is that you need to respect the capacities of each of the edges. Each edge is sort of a pipe and it has a capacity which is a non-negative number, and you can only push that much flow through, at most that much flow through that pipe. Right, cool. That's the flow problem. And then so again उसके बाद फिर then I think you learned about the greedy algorithm for the flow problem to find the maximum flow, which is that you try pushing as much flow as you can, as long as you can still push more flow. You keep doing it until you get stuck. उस point पे you learn that greedy is not good enough. You see an example, I think, which shows that there is a way to push flow systematically that's more optimal compared to pushing flow greedily, which is that find a path, push flow, and keep going. उसके बाद what you do is you learn about the residual networks. Residual networks are nothing more than giving you an undo key, right? At each edge you put, whenever you push a flow through an edge, you add a reverse edge, which is nothing more than an undo key, which tells you at any later point, if you want to undo that flow that you pushed through a particular edge, you can undo it, right, by that reverse edge. That's the residual network. And then you learn that that's actually that works, right? Greedy with an undo gives you the optimal flow. But उसमें क्या issue था? That's the Ford-Fulkerson algorithm, I think. है ना? Right? You guys proved that it's correct. It gives you the optimal flow, maximum flow, है ना? Using the cut flow duality theorem, right? Whenever you have a flow which is equal to a cut value, it must be equal to the maximum flow, because the flow cannot be more than the minimum cut. Flow cannot be more than the minimum cut. It has to be less than equal to the minimum cut, right? Okay, so you have an algorithm which gives you an optimal flow, but there's a problem with that algorithm, which is what?
एक ही path पे वो सिर्फ check करता है, हमें पता नहीं है कि कौन सा path बोलेगा.
Right. So it could kind of keep using the same path multiple times. So if your flow, I think उसकी जो typical example है, that's कौन सी वाली है? इस तरह की कुछ. I don't remember, मैंने अब flows नहीं देखे, काफ़ी देर हो गई है. इस तरह की कुछ example बनती हैं. I think you keep 4 of them equal to 1 and 1 of them equal to 1 million or something. I think this is the one that you keep equal to 1 million. Right. Is it true? नहीं. हाँ. इसको 1 के इक्वल कर लो और इसको 1 मिलियन कर लो. Right. Did you see this example or something similar to this example? Right. So, इसमें Ford-Fulkerson will give you the correct flow, which is equal to, I think, 2 million. But it could fail. It could keep doing it multiple times. It could find, for example, this path. This key flow value is 1. Right? Yes, no? If I use, for example, let me name them. S A, B, T, right? It could find this path, which gives you flow equals to 1. ऐसा करोगे तो you'll have to add this residual edge, which has value 1, which means that in the next step, you could use this path, which is S, B, A, T. This one also has value equal to 1, right? ऐसा करोगे तो फिर you will have to add residual edge back. Or फिर दोबारा you will find this, and then you will find, you will iterate between these two paths a million times. You will find the actual flow, which is 2 times a million, but you'll do it in this much time, right? You'll have to try this many iterations, right? Which means इसकी जो time complexity, it's dependent on the edge capacities, which is bad, which is not good, right? You want your time complexity to depend on the size of the input and not the value of the input, right? ये problem है इस algorithm के साथ. And then you find out that we can solve this using what? You solved this problem, है ना? Yes, no? Raise hand if you were here last time, last Wednesday. Just to, I don't know, pulse check karo mein. Okay, people were there. Okay, cool. Did you see this problem? Raise hand if you saw this problem. Discuss. Okay, cool. This was discussed. Did you see a resolution to this problem? How do we solve this problem? Okay, probably that was not discussed. The way we solve this problem is, so how do you find this path? How do you find one path from S to T? What? DFS. You use DFS, right? If instead of using DFS, you use BFS, that's it. That's the key. That solves your problem. That will make sure that. So I'm not. Plan was not to go through the flows. I think I'll ask Dr. Imdad to do a short video or share with you, probably this week. But BFS solves this by finding the shortest path. Okay, so every time you are finding a path from S to T, you are using BFS. You are finding the shortest possible path. Okay, every time you find a path, there is a critical edge. There is a bottleneck edge. There is an edge which gets saturated, right? This case में this is the edge जो यहाँ पे हम कर रहे थे ना, this was the edge which was getting saturated, right? So BFS के case में what you are going to do is you are going to add a reverse edge on that particular saturated edge, the bottleneck edge जिसकी capacity को आपने completely exhaust कर लिया in that particular path. All right, cool. इसका मतलब ये है कि at a later point you are going to use the reverse edge, जैसे कि हमने यहाँ पे किया था, this one, right? And that's all right, and that's allowed. But if you use BFS and you use a reverse edge to find shortest path again, तो फिर second time आपने जो shortest path find किया उसकी length पुराने वाले shortest path से ज़्यादा होगी. Because now we're using a reverse edge. You remember the BFS tree things? You start with a node S, and then S के जो immediate neighbors हैं, they are immediate neighbors of S in the graph. Or then you have nodes which are at distance 2 from S, right? And so on, okay? So, and then there's T somewhere here, okay? At any point you use, let's say this is a saturated edge, okay? At a later point, what you're going to use is a reverse edge of this edge, okay? है ना? So this edge, ये जो इसका reverse edge है ना, ये आपने बाद में add किया. अगर आप BFS use करें, तो somehow in a later path, do I have colors somewhere here? At a later path, you somehow, by some path, came to this node and went up again and then found some other path to T, right? That's how you find a shortest path that uses the reverse edge that you added, है ना? This new path must be of length more than the original one, because instead of coming directly from S to T, here, then here, then here, then here, and then here, you came to level 2, and then you went up, right? And then you came back to level 2, 3, 4, up till you reached T, right? Which means the second time you found the shortest path to T using the saturated edge, you found a path which was of length at least one more than the previous one. So we cannot do that. Okay. So her solution is that instead of doing this, what if we make sure that we don't go to the same node again, right? The thing is, flows may, you have to allow the undo thing. अगर undo thing allow नहीं करेंगे तो you won't be able to find the optimal path. You can mess up when you are trying to find a path. There's no more strategical way to push flow from S to T. You have to find a path, and then at a later point you should be able to figure out कि ये वाला जो मैंने edge use किया था ये मुझे use नहीं करना चाहिए था. That was a bad idea. For example, यहाँ पे if you go from S to T, you go from S to A, and A to B, and B to T, right? Using this edge A to B was a bad idea. We added this edge B to A because we wanted to implement the undo thing, that we should be able to figure out कि अगर मैंने, we didn't just implement this, we implemented everything. We implemented undo of every possible edge. ये वाला edge भी हमने undo add किया, इसका भी हमने undo add किया, right? For every possible edge that we used, we add an undo edge or residual edge for that. And that's necessary because we can make mistakes when we are doing DFS and BFS. Yeah.
Why would the second path cost more than the first one?
Cost in terms of the number of edges.
Like you yourself said that the second path would be longer than
The original one. Longer in terms of number of edges, not in terms of the capacities.
hops.
In terms of number of hops, yes. Right? Because that's how BFS works, right? If you use a shortest path, और उसके अंदर एक edge था, next time you use shortest path that uses the reverse of that edge, तो दूसरे वाला path उससे बड़ा होगा. just because of the reverse edge, right? ये वाला जो BFS tree है ये तो नहीं change हुआ ना, आपने सिर्फ इसके अंदर ये वाला edge add किया, right? Which means that you somehow came from S to neighbors, उसके neighbors, and then you went back, and then you came back, which means that you are using a path which is using more edges, right? Right? Okay, so this argument shows कि if you use shortest path, तो फिर एक edge को अगर आप next time use करेंगे तो shortest path की length ज़्यादा हो जाएगी, है ना? पर shortest path की length कितनी ज़्यादा होगी? What's the maximum possible length of a shortest path in a graph? Yeah, it's all the edges, which is n minus 1, right? n minus 1 से तो ज़्यादा नहीं हो सकती ना. You can go through every vertex and your path length would be n minus 1, है ना? Which means कि आप एक edge को n minus 1 से ज़्यादा times नहीं use कर सकते, right? So if you use BFS, you cannot use the same edge and more than n minus 1 at a time. And there's your guarantee on the number of times that you have to do this step, right? That kind of avoids the unwanted situation where you have to use the same edge. Like for example, यहाँ पे हमारे पास we had 5 edges, 4 nodes, and we were using this edge 2 million times. This would be impossible when you use BFS, right? BFS makes sure that you won't be able to use this edge more than n minus 1 times. You won't be able to use this same edge 3 times. We never use it, but the guarantee is that you won't be able to use it more than 3 times. I have 4 vertices, right? Yeah. You have a question?
Aren't we adding reverse edges in there? Then don't the number of edges go up?
The number of edges, so एक edge के लिए you can add one more edge, right?
तो n minus 1 into 2 नहीं हो गया number of edges?
So n minus 1 is so n is the number of vertices, and n minus 1 is the length of the longest path in the graph. So number of nodes आपके same रहेंगे, है ना? So a path from S to T can be at most n minus 1, where n is the number of vertices. You can add as many edges as you want. That's not going to change that. Your guarantee would still remain n minus 1, where n is the number of nodes, not edges, right? All right, I think so. I think Dr. Imdad will do more justice to this topic in his video, okay? So, but I kind of gave you a summary. Any questions before we move to the NP-Completeness thing? Yes? All right, okay, cool. NP-Completeness. So same set of slides, but हमने एक दो reductions करनी है जो last time नहीं की थी. And I also wanted to go through the reduction that we were doing in the last worksheet, okay? Before we do that, what kind of problems I want you be able to solve in your final exam related to NP-Completeness, right? That's the kind of question on everyone's mind. Let me answer that. There are 4 different kinds of problems that can appear on the exam. One type of problem is, I'm going to list it, I'm not going to write it, okay? One possible problem is, I'm going to tell you the problem name, and you will describe the problem for me. Okay, I'll say describe vertex cover, and you will kind of describe complete vertex cover problem for me. What's its input and what's going to be its output. Okay, that's a typical problem which everyone should. This is kind of iman ka sabse niche wala darja. Okay, you should be able to do this. Everyone should be able to do that. Okay. Second problem, you should be able to prove a problem NP. Okay, you should be able to prove that you can verify the yes instance of a problem in polynomial time. Okay, that's the second problem. Cool. अब मैं सोच रहा हूँ कि चौथा कौन सा था क्योंकि मुझे तीसरी याद आ रही है. Okay, third is I think the third one is to be able to give me a plan to prove how to prove a problem NP-complete. Okay, I give you a problem. I'm not asking you to prove it NP-complete, but I'm asking you, if I were to ask you to prove it NP-complete, what would be your plan? What would be your steps? For example, you could say that I'm going to prove it in NP, then I'm going to prove it to be in NP hard by reducing it from this particular problem, and that would complete my steps. Okay, so outline of your plan. If that plan has some concrete steps, you will get marks for that. The last and probably the most important part is that you should be able to reduce it from a known problem. Okay. All right. So I think they kind of build each of these steps build on the previous steps, but these are the 4 things that I think you should be able to do that. 1, to be able to describe all of the problems that we have discussed in class. Okay, you should know SAT, you should know 3 SAT, you should know 3 colorability, you should know vertex cover, you should know maximum independence set, clique problem. What else? Whatever problem we discuss in class, you should know that. Okay. Second, you should be able to prove the problem is in NP. Third, you should be able to give a plan how to prove a problem to be in NP complete. And the fourth, you should be able to give me a reduction from a problem to your problem. All right. Any questions? Yeah. दोनों cases हो सकते हैं. It's possible that I give you a problem and I ask you to reduce it from this problem, or I just ask you to prove it to be an NP hard problem, and you have to figure out which problem I have to use to reduce it from. Yeah. Good question though. Are we good? Should we move on? All right. First, I think this is where we were. So we described SAT, we described 3 SAT. We reduced SAT to 3 SAT. This is what we did last time. और vertex cover को हमने define किया था, और our plan next was to do this, to prove that vertex cover is NP hard by reducing 3 SAT to vertex cover. Okay, so that's where we're going to start today. All right. Any questions before I become invisible? So, can anyone describe vertex cover problem for me? Quickly, what's the input of vertex cover and what's the output? Okay. Sorry, input क्या है?
The graph.
Input is a graph. थोड़ा सा इसको वो कर लो. Undirected, directed, weighted.
Undirected.
Undirected graph. Okay. Okay. Unweighted, undirected graph. And
the output would be the set of vertices that we need to cover.
यहाँ पे I think you need to दोबारा सोचो.
Vertices which cover the entire set.
Entire what?
The entire graph.
That are connected to all of the edges.
Yes. Okay. That's good. But in 3 attempts. Okay. So vertex cover problem says that given, so I'm writing graph here, but in your exam you're going to write unweighted, undirected graph. Okay. So given a graph G, does there exist K vertices graph in a number K, okay? That सी टेक्निकल चीज़ें यहाँ पे, ये अपने गलतियाँ नहीं करनी. That cover all edges. Okay, so that's the vertex cover problem, and our goal today is to prove that vertex cover is at least as hard as 3 SAT. Okay? How do we do this? How do we show this? How do we show this? That's gonna be my theorem today. How do we show this? What does it mean to be able to show this? So what is अच्छा, different perspectives होते हैं. I think one way to look at this reduction is that I'm interested in an algorithm. Okay. So this actually means an algorithm. अब इस algorithm की जो input है is input of 3 set. Okay. यहाँ पे मुझे instance लिख लेना चाहिए. That's going to be the more appropriate word. Instance of 3 set. Okay. और इसकी जो output है, what is it? What's the output of this algorithm? Anyone? क्या? So मैं इसकी बात कर रहा हूँ. If I'm able to reduce 3 set to what is covered in polynomial time, I'm saying that it's equivalent to saying that I have an algorithm which takes input an instance of 3 set and spits out input of vertex cover. Yes. Okay. So it takes the input of 3 set and outputs input of vertex cover. Okay. It transforms the input of 3 set into an input of vertex cover. That's what it does. Okay. Right. I think the only difference of this algorithm has with the algorithms that we have studied so far is that we don't care about the time complexity of this algorithm as long as it's polynomial. Okay. As long as this algorithm takes polynomial amount of time, we are okay. We don't want to make it more efficient. We don't care about making it more efficient. Yeah.
What if we go the reverse way and try to create an algorithm that takes an instance of the cover problem and turns it into an instance of
That would, okay, so he says that if I am able to design an algorithm which takes an instance of vertex cover problem and spits out instance of 3 set problem, that would prove the reverse of this. That would prove a reduction from vertex cover to 3 set. And that's a valid thing to do. Alright, so that's our goal today. Okay. अच्छा, ये कुछ भी हम कर सकते हैं ना, कोई भी हम instance vertex cover का return कर सकते हैं. But what's important is कि let's call this thing x. Okay, the instance of the 3 set which is given as input to my algorithm, or the instance of vertex cover को हम y कह देते हैं. Okay, what's the requirement is that if x is a yes instance, then y must be a yes instance. Okay? Okay? If the input of 3 set that I'm giving you, if that is satisfiable formula, then the graph that you are outputting must have a vertex cover of size at most k. Okay, that's the requirement. अगर ये requirement ना होती तो I can just spit out any vertex cover instance, right? Are we clear? This is an extremely important point. I think ये वाला आप नहीं समझ पाएंगे तो फिर you're going to have trouble in exam. क्या?
Would the instance of vertex cover be a graph?
Yes. Instance of vertex cover is always a graph. Instance of vertex cover is a graph and a number k. Okay? That's an instance of vertex cover. And the instance of 3 set is a 3CNF Boolean formula. Okay? Cool. Questions? Okay, yeah.
Can you repeat that again? If x is a yes instance, then y not.
So question क्या है?
Like, can you explain that again?
So, अब देखो जो 3 set का instance है ना, both of these problems are decision problems, which means that the instance that I'm giving you of 3 set, it could be a yes instance, it could be a no instance. Okay? If I give you a 3 set instance which is yes instance, your algorithm should output an instance which is a yes vertex cover instance. If I give you an instance which is not satisfiable, which is a no instance of 3 set, your algorithm should spit out a vertex cover instance, a graph in a k that's not, the k is not K size का vertex cover नहीं होना चाहिए उसमें. That should also be a no instance. Okay, so that's the requirement. Are we good? Okay, cool. So that's what we are going to do. We are going to find a reduction or an algorithm. इस तरह के algorithm को reduction कहते हैं. That's the name of this algorithm, reduction. Okay. Did I use the board underneath? नहीं किया मैंने. Okay. All right. So cool. मुझे थोड़ा सा सोचना पड़ेगा. So my input is a formula of this form. Okay. इसके अंदर कुछ variables होंगे, literals होंगे, उनके दरमियान और हो रहा होगा, उसमें कुछ negations भी होंगी और multiple clauses होंगी. Okay. So एक दो चीज़ें मैं formalize कर लेता हूँ. एक मैं ये कह लेता हूँ कि the number of variables is n. Okay, it helps to name things. I'm just naming things. Number of variables is equal to n. Number of clauses, इस तरह के clusters, is m. All right, and now I have to construct a graph out of this. And that graph should have a vertex cover of size at most k, if and only if this formula is satisfiable. Okay. All right. So what do we do? Cool. One simple thing जो मुझे अभी नज़र आ रही है वो ये है कि if I create an edge. Question? बोलो. Talk to me. Yeah. Clauses. So this thing is called a clause. Okay. 3CNF में you have three literals जिसके बीच में और हो रहा होता है, उस combination को clause कहते हैं. So इसके अंदर यहाँ पे एक, दो और तीन clauses हैं. इस number of clauses जो इस formula में होंगी उनको उसका नाम मैंने m रख दिया. 3 sat में m होंगी, but each clause has 3 literals. Okay, अब उसके साथ उसको confuse कर रहे हो. Okay, so you can have as many clauses as you want, but each clause has exactly 3 literals. Okay, क्या? यहाँ पे n is equal to 3, लेकिन अगर मैं for example यहाँ पे x4 इंट्रोड्यूस करवा देता हूँ और यहाँ पे x5 करवा देता हूँ और x6 करवा देता हूँ तो फिर 6 हो जाएगा. इन द होल फार्मूला आपने देखना है कि कितने वेरिएबल हैं. 3 सेट के हर क्लॉज में एग्जैक्टली 3 होंगे. पूरे फार्मूला में यू कैन हैव अ लॉट मेनी वेरिएबल्स, है ना? यस, ओके. If the problem is clear, let's move to the reduction. Okay, so I have to construct a graph out of it. और अभी मेरे ज़हन में कुछ भी नहीं है कि कैसे करेंगे. Okay, so give me. मुझे कुछ voices आ रही हैं. कहाँ पे है? मनीष, doors तो close कर दो यार. Thanks. Okay, so I have to construct graphs. और मैं ग्राफ्स के अंदर नोट्स बनाऊंगा और नोट्स और एजेस बनाऊंगा. दैट्स व्हाट अ ग्राफ इज, राइट? और उसके बाद फिर मुझे बताना पड़ेगा कि के क्या चीज़ है ना? ऑलराइट. Okay, so what I understand from vertex cover is that whenever I add an edge between two vertices, I must pick one of those vertices. है ना? क्योंकि उस edge को मैंने कवर करना है ना? Okay, so if I do this, if I add if I define two nodes, उन nodes के मैंने नाम रख दिए कुछ भी xi और xi bar और उसके बीच में edge रख दूँ, तो whatever vertex cover algorithm someone has, they are going to have to pick one of them. Okay, that seems like a reasonable thing to do. Okay, but hold on, अभी मैं बहुत unreasonable चीज़ें करने जा रहा हूँ. Okay. cool. If I do this for every variable, तो फिर that will make sure कि मुझे कम से कम कितने नोड्स पिक करने पड़ेंगे अपने वर्टेक्स कवर में? No. n, because there are n variables, और हर variable के लिए I'm creating 2 nodes, right? So I have x1 bar, x2 bar, x3 bar, and so on, right? So for every edge I have to pick one vertex, which means that I'm going to have to have at least this many nodes in my vertex cover. इतने edge तो मैंने cover करने ही करने हैं. Yes. वेरिएबल्स मैंने नहीं इंट्रोड्यूस करवाए. सो देखो, इस तरह की कोई चीज़ मेरे एल्गोरिथम को एज एन इनपुट मिलेगी. उसकी शक्ल कैसी है ये मुझे नहीं पता. वो मुझे जब मेरे मिलेगी तब मुझे पता चलेगा. ओके अब मेरे एल्गोरिथम ने डिसाइड करना है कि मैंने उसे ग्राफ कैसे कंस्ट्रक्ट करना है. ओके इसमें जो नंबर ऑफ़ वेरिएबल्स हैं उसका नाम मैं रख सकता हूँ, है ना, और नंबर ऑफ़ क्लॉजेज हैं उसका भी मैं नाम रख सकता हूँ. तो मैं ये कह रहा हूँ कि n इस तरह के डिसजॉइंट एज मैंने क्रिएट कर दिया. ओके दैट मेक्स श्योर्स कि ये जो ग्राफ, अगर मैं यही चीज़ मैं ग्राफ स्प्लिट आउट कर दूँ तो दिस थिंग हैज़ अ वर्टेक्स कवर ऑफ साइज n से छोटा नहीं है इसका. ओके n का है, n आई कैन पिक सम ऑफ द वर्ड्स और दैट विल कवर एवरीथिंग इन हियर. ओके ऑलराइट कूल. अब मैंने क्लॉजेस का कुछ करना है. What do I do? So, right. This is kind of an unreasonable thing, okay? Until I tell you, I think you are kind of blind in this regard. मुझे लगता है कि it's gonna take you weeks probably to figure out what I'm going to tell you next, if I don't tell you the next part. तो इसलिए मैं इसको थोड़ी सी unreasonable चीज़ कह रहा हूँ. बोलो.
Why are we taking complements and then joining them? Is it about
So the idea is कि either the variable itself or its negation should be true, है ना, in the SAT formula. मैं उससे equivalent कोई चीज़ अपने ग्राफ के अंदर बनाना चाह रहा हूँ. उसके इक्वलेंट जो चीज़ मुझे नज़र आ रही है वो ये है कि आई टेक अ नोड और इट्स नेबर इन माई वर्टेक्स कवर. ओके काइंड ऑफ क्रिएटिंग इक्वलेंसेस बिटवीन द बूलियन फार्मूला एंड द ग्राफ दैट आई एम क्रिएटिंग. ओके cool. Okay, so the next thing is this, that I create a triangle for each class. Okay, so a class is going to have 3 literals, L1, L2 and L3. These are either one of these, या x कोई xi होगा या xi का complement होगा. Same for L2, same for L3. Okay. All right. If I do that, vertex cover requires कि at least 2 of them are in my vertex cover, है ना? If I give you a triangle, you must pick 2 vertices out of that triangle because there are 3 edges and you have to cover them. Okay? कोई भी एक, for example, if I pick this thing in my vertex cover, तो फिर ये वाला edge cover नहीं होगा, है ना? So 3 vertices I can of course cover, लेकिन 2 से भी हो जाएगा. Okay? If I pick any 2 vertices in my vertex cover, a triangle will be covered. Okay? Next part is, I think, somewhat reasonable. So I expect someone to figure it out. कि हम क्या कर सकते हैं. So I create a triangle for each clause. Okay, so थोड़ा सा मुझे इसको generic करने दें. Let me call this Li, Lj. अब मैं इसको K नहीं कह सकता K क्योंकि मैं वहाँ पे use कर रहा हूँ. What do I use? LP कर लेते हैं इसको. Okay. So I create a lot of triangles, one for each class. Which means I'm going to have to pick 2 vertices from each of them, which means कि वर्टेक्स कवर का साइज एटलीस्ट कितना होगा?
What do the vertices here represent?
सॉरी व्हाट?
What do the vertices here represent in these triangles?
So the vertices in each of these triangles represent the literals in the original clause. Okay, so this triangle represents, let me call this Li1, Lj1 and Lp1, and this is, let's say, clause 1 जो यहाँ पे है, for example, and this is clause 2, this is clause 3, and let's say I'm going to have clause M, right, because there are M clauses. So I'm going to have M triangles. Okay, that's not it. I'm going to थोड़ी सी और reasonable, हाँ अब चीज़ें reasonable होंगी मेरे ख्याल में, ये वाली चीज़ इतनी reasonable नहीं थी. Okay, so अब मुझे ये बताएं कि if this is your graph, if I spit out this, what's the size of the vertex cover? Absolutely. Okay, cool. Everyone should be clear on this. It's n plus 2m. बोलो.
I agree with this, but repetitions ही होंगी दोनों.
If you are saying that I have some literals ऊपर भी और नीचे भी, तो yes. So it's possible that this Li1 is actually x1 के equal है. होगा, definitely होगा. But I'm creating two different nodes for this. If I have to, I'm creating two different nodes for that. Okay, I'm doing something more too, जो मैंने अभी करना है. But so far, this should be perfectly clear कि ये वाला जो graph है, इस graph का vertex cover has size n plus 2m. It's not less than that, it's not more than that. It's exactly n plus 2m. क्या?
L and X are separate.
दोबारा बोलो.
So like for X and X bar, and so you have L and all that.
Right. So yeah, so we are a bit confused about the L's and X's. So this is the clause. Okay, this clause may I have x1, x2 bar and x3. So this Li1 would be x1, and this would be x2 bar, and this would be x3. Okay, so इस फार्मूला में they could be equal to x1 or x1 bar and so on. I'm just giving them names because clause के अंदर जो चीज़ें हैं उनका नाम literals हैं.
So like did we count these X's ऊपर जो हमने notes बनाए?
हाँ, but I'm creating them separately. Okay, so if I have an x here, I'm going to create a new x here. If it appears in some clause, if it, for example, x1 appears in 7 different clauses, एक दफ़ा वो यहाँ पे आएगा और 7 different clauses में यहाँ पे आएगा. So it would appear 8 times. All right? Okay, so it means, so do we all agree that this is the size of the vertex cover in this graph? Yes, no? People who agree? Okay. People who don't agree, why? What's going on? Why not? Let me help you. We have time. I have to rush through this. Yeah? So, okay, so n is the number of total variables जो इस formula में है, and for each one of them I'm creating a separate edge. That's all. Triangles are separate. Okay, so for example, triangles में I don't care कि n कितनी, triangles का n से कोई ताल्लुक नहीं है. So I'm creating m triangles, and n separate edges. So triangles में वो variables ज़रूर आएंगे, but I'm not saying कि उनको ऊपर मैंने create किया तो दोबारा नहीं create करूँगा. I'm just 2m करने से वो सारे कवर नहीं होंगे क्योंकि ये वाले एच मैंने सेपरेटली क्रिएट किए हैं. लेट मी डू इट फॉर वन पर्टिकुलर फार्मूला. ओके, सो इसके लिए कर लेते हैं. ओके, सो यहाँ पे ऐसे करते हैं x4 और x3 और x5. ओके, x3 का बार कर देते हैं और यहाँ पे x5 और x3 कर लेते हैं और x6 कर लेते हैं. Okay, so if this is the situation, my graph so far is going to look like this. I'm going to have x1 bar, x2 bar, x3 bar, Oh boy, this is a lot of writing. X5 bar, x6 bar. Okay, और उसके बाद I have 3 different triangles. I have a triangle which has x1, x2 bar, and x3 bar. So a separate copy of x1 node here. Okay, and then I have a triangle which is x4, x3 bar, and x5. Another triangle which has what is it? x5, x3, yeah. Okay, and x6. Okay. All right. So यहाँ पे इस फार्मूला में n was equal to 6 and m was equal to 3. And over here इसका जो vertex cover है उसका size 12 होना चाहिए. Okay. So you need 6 vertices to cover these edges, and you need 2 vertices per triangle to cover the triangles. All right. Okay. Yeah. It's n plus 2 times m. For each variable, I created an edge. So for each variable, in my formula, I need a node to cover that edge. Right? And for each clause, I need 2 vertices to cover the triangle. So it must be n plus 2m, which is 6 plus 2 times 3. Yeah.
What if one of the vertices are repeating in the clause?
मैंने इसको कुछ कर दिया क्या सॉरी
What if one of the vertices are repeating in the clauses? Like if I select x,
we usually prohibit that. So आप ये कह रहे हो कि for example यहाँ पे x3 2 दफ़ा आ रहा है.
नहीं, मैं कह रहा हूँ कि अगर हमारी पहली x1 और x कॉम्प्लीमेंट है, x1 कॉम्प्लीमेंट,
Yes.
उसमें से फॉर एग्जांपल मैं x1 ले लेता हूँ
Yes.
और जो हमारा क्लॉज है x1, x2 बार और x3, उसमें से भी x1 और x2 बार ले लेते हैं.
Right.
तो वो एक तो रिपीट हो जाएगा. तो ये जो हमारा k n plus 2 है, ये अपर बाउंड है या फिर एक फिक्स्ड है?
No, it's fixed. और उसकी रीज़न ये है कि this is a different copy of x1. It's not the same vertex. Okay? इसका अगर आप नाम डिफरेंट रखना चाहते हैं तो आप रख सकते हैं. Call it c1 x1 if you want. Okay? But it represents the fact that the x1 appears in that class, but it's different from the x1 node that I created here. Okay? Cool. Yeah.
And sir, we also discussed that yes, SAT problem has to translate.
वो वाला काम हमने अभी करना है. वो हम अभी से एक दो स्टेप हैं दूर. Okay? अच्छा, moving towards that step, which is that we need to make sure that if this formula is satisfiable, then this construction should have a vertex cover of size n plus 2m. वो यहाँ पे अभी तक वैलिड नहीं है क्योंकि this graph has always n plus 2m vertex cover size, है ना? है ना? We need to make sure कि अगर वो वाला फार्मूला सेटिस्फाइबल नहीं है, ये वाला पार्ट हमने करना है. ओके? क्योंकि अभी तक तो ये है कि ये ग्राफ हमेशा इसका साइज n plus 2m है. राइट? We need to make sure कि if this is not satisfiable, then this graph does not have a vertex cover of size n plus 2m. ये वाला काम हमने करना है. Right? So how do we force that? How do we force, in essence, if some of the clause is not satisfied by a particular assignment, तो फिर that clause does not cover the vertices that we described, does not cover the whole graph, right? Which means कि हमने कुछ edge add करने हैं इसके अंदर. Okay? Let me do that, okay? और उसके बाद मैं explain करता हूँ. Before I do, does anyone has any idea कि कैसे कर सकते हैं? If you turn off your computer screens, so I'm going to give you 2 points if you describe what I'm going to describe in next 5 minutes. So I'm going to add some edges which will make sure that if this formula is not satisfiable, then this graph does not have a vertex cover of size n plus 2. Okay? How do I do it? How do I make sure that this happens? Yeah.
Add some edges from the first graph to the top, like from the literals to the clauses.
Okay, which one?
Give me an
Socho. You have time. You want to say something? Yeah.
Add some edges in between the triangles which correspond to k. अगर sat वाली प्रॉब्लम में वो वेरिएबल 1 है तो वहाँ पर in between
ये वाला काम थोड़ा सा ट्रिकी है. You remember ये वाला part. Your input is an instance of 3 sat, which means कि आपको नहीं पता कि कौन से वेरिएबल्स को 1 रखना है या 0 रखना है. You just have a formula in front of you, right? You have an instance of 3 sat, and that you can use in the algorithm. बोलो. You are not very far off from truth. Not that there is anything interesting on the slides, but क्या?
literal वाले ग्राफ से वो एज बना दें जो like क्रॉस में x1 है और like पहले ट्रायंगल में x1 तो उन्हीं में से
Okay. So what do I do?
like वो पहले x that x1 with x1 का x1
Okay. Or
next to that और यहाँ
or x2 bar से x2 bar, or x3 से x3. Okay. Or x4 से x4, x3 bar से x3 bar, x5 से x5, x5 से x5, और x3 से x3, x6 से x6. Did I add all the edges? Okay, I think I did.
You took x3 bar, x3
X3. Oh, yes. Sorry. Let me just quick pass by this and come here. Is this the only mistake I made? Looks like it. Okay. Does it do the trick? Oh, first of all, if I add edges, vertex cover का size बढ़ सकता है, कम नहीं हो सकता, right? Because now I have more things to cover, है ना? So if I add edges to a graph, my vertex cover size can only grow.
What if just x1 की जगह हम directly x1 input करते हैं without any
We can do, I think, so here's, let me just give you the next thing. It works, but I have to prove it does. To it works. That's what we were supposed to do. Yeah, it works, but why does it work? By saying that it works, I mean to say that if the original graph is original formula I gave you through this algorithm is satisfiable, then this graph has a vertex cover of size n plus 2m. If the original formula is not satisfiable, then this graph cannot have a vertex cover of size n plus 2m. Okay, now you have to prove why it's true. The onus is on you. You are claiming 2 points. I mean, I'm going to give you 60 seconds if you want to kind of think through your solution.
For every clause term I set हमें वही vertex we will be forced to choose that vertex in our VC problems. तो
क्या?
अगर P set में वो possible नहीं है solution तो यहाँ पर एक edge skip हो जाएगा. तो for example I में तीनों vertex
Okay, so you have to show 2 directions. Let me just, because I want to formalize this. First direction is if phi is a yes instance, then there exists a vertex cover of size n plus 2m, right? ये वाला part. Okay, how do you prove this? Go ahead. If the original formula is satisfiable. So those steps. Think about it and while I write down the second step, okay? The second step is, easier version of the second step is that if there exists the contrapositive of the statement that we're trying to prove, if there exists a vertex cover of size less than or equal to n plus 2m, then phi is a yes instance. Okay, so these are 2 parts that we have to prove to complete the reduction. First of all, do we agree that these are the 2 parts that we have to prove to make sure that the reduction is working? There's actually the third part, which is kind of trivial in this case, which is that doing this takes polynomial time, but it's trivial, right? You can look at the formula and you can construct this graph easily. Okay, cool. Part A. How do we ensure a part A? You guys want to say something? Yeah, go ahead. So all I'm doing is if a variable appears in a clause, उसके साथ मैंने इसको connect कर दिया by an edge. So x4, x3 bar and x5 appear here. So I connected x4 with x4, x3 bar with x3 bar, and x5 with x5. That's what I did. Okay? Come on, go ahead. I don't want you to go empty-handed. Yeah. You can share a grade with someone if someone else does the work for you, the remaining work for you. Yeah, go ahead. So देखो इस बोर्ड के ऊपर जो कुछ भी है वो एक ग्राफ है, उसकी वर्टिसेस हैं, ठीक है? यहाँ पे यहाँ तक जो कुछ था वो फार्मूला था और वेरिएबल्स थे. इस ग्राफ के अंदर जो वर्टिसेस हैं उनके नाम मैंने ऐसे लिखे हैं कि हमें इसके और इसके बीच में कॉरेस्पॉन्डेंस बनाना आसान हो जाए. Okay? Everything in here is a vertex or an edge. Okay? We're just making correspondences. यहाँ पे मैंने you can name them any way you like. I don't care, or no one cares actually. But all I'm saying is that this somehow represents the variable x1 in here, this node. But these are all nodes. यहाँ पे variables कोई नहीं है. क्या? हाँ. Okay, so the way I think you should think about it is when I say a formula is yes instance, what does that mean? It means there is a way to satisfy that formula by assigning values to the variables. है ना? I can set values to the variables that satisfies every clause in the formula. That's what it means that phi is a yes instance. Okay? If this happens, then I have to figure out a way to find the vertex cover in this graph of size n plus 2m. Okay? So, up this point pe you can assume that these are the variables that I can set to 1 and these are the variables that I can set to 0 to make sure that phi is satisfiable, right? because phi is known to be satisfiable if phi is a yes instance, right? Now I have to figure out if I can set some of these variables to yes and some of these variables to 0 and some of these variables to 1, some of these variables to 0 and some of these variables to 1. Then this graph has a vertex cover of size n plus 2m. Did I confuse you? Did I succeed in confusing you? Bolo?
तो k is equal to n plus 2 में हम सारे ones को add कर रहे होंगे.
Okay, so देखो, before I added these blue edges, I had no problem in my word, है ना? I knew which nodes to pick to make sure that this graph has a vertex cover size n plus 2m, है ना? We all did, है ना? We all agreed on that. I made sure we spent 5 minutes agreeing on that, है ना? The problem now is that the blue edges should be covered only if those particular variables are set to 1 that make the formula satisfiable. Okay, so now I have to somehow cover blue edges. Okay, how do I cover the blue edges? What's the problem covering blue edges? Discover the problem that I have when I'm trying to cover the blue edges. जो white edges हैं वो तो मैंने cover कर लिए है ना? I pick 2 vertices in a triangle. I pick 1 vertex in the edge I had, and they cover all the white colored edges, है ना? है ना? Remember, this is what I did. Do I have a different color? I have. Okay, so मैंने ये कहा था before I had blue colors कि pick 2 of these and they will cover all the edges here. Pick one of the, I don't know. अब यहाँ पे मैं जो करने जा रहा हूँ, that's gonna kind of push you in a certain direction. Pick one of the edges, one of the nodes in here, one of the nodes in here, one of the nodes, and they'll cover the edges. And now pick 2 vertices from each triangle, and you're done, right? These are the n plus 2m vertices which cover all white edges, है ना? ठीक है, so far so good. But now I have a problem. The problem is that some of the blue edges are still there, है ना? They're not covered. ये वाला blue edge cover नहीं हुआ, है ना? And I need to make sure that this blue edge is coverable if the original formula is satisfiable. Okay, that's the problem. Go ahead.
So for example, in the first case, हम x1 को ही choose ही करेंगे because x1
हाँ.
ही true है.
हाँ.
So if we pick x1, तो हमारा blue वाला भी
Right,
cover होगा.
right. क्या?
So in every case, we'll only pick that particular edge out of the 2 जो कि true है.
Absolutely. That's the punchline. She did it for me. Okay. So if the formula is satisfiable, तो फिर उसमें से कुछ variables होंगे जो set to true या set to 1 होंगे. Okay. If I pick that particular literal in my vertex cover. So for example, if x1 is set to true to make the formula satisfiable, then I should not pick x1 bar. I should pick x1 in my vertex cover. Okay, and this edge from x1 to this class was represent the fact that this x1 makes this class true. Okay, if x1 makes this class true, I don't need to pick the node in the class triangle. उसके अलावा जो 2 vertices हैं, that can cover the vertices in the triangle. All right. So if I pick the vertices जिनके variables true हैं, and I pick the negation of the vertices जिनके variables false हैं, this formula becomes so this graph becomes a yes instance of vertex cover if the original formula was a yes instance of the 3-set problem. Okay, so let's have a discussion now. क्या You share the credit with him, okay? इन दोनों के रोल को ले लें. They're gonna get 1 absolute point each. हाँ, okay. क्या? Go ahead. Thanks.
तो फिर हमारी
No clapping for them. Nothing. Thank you. Okay.
हमारी शुरू वाली इंट्यूशन ये गलत थी कि हम सारे ट्रू वर्सेस को क्यों पिक कर रहे हैं उसके अंदर जब एंड हमने पिक किए थे.
Repeat करो. Sorry.
जब हमने शुरू में जो सिंगल एज में से हमने x1 और x1 बार में से एक पिक किया था वो हमने इस बेसिस पे पिक किया था ना कि उनमें से ट्रू कौन सा है.
Yes.
तो फिर हमारी वो इंट्यूशन गलत है कि हम वो ट्रू क्यों पिक करें. हमें तो ओवरऑल देखना चाहिए कि वो ओवरऑल सेटिस्फाई करता है कि नहीं.
Okay. So जो ब्लू एच ऐड करने से पहले हम वर्ड्स पिक कर रहे थे वो हम आर्बिट्रेरीली पिक कर रहे थे. उससे कोई फ़र्क नहीं पड़ता. अगर ब्लू एच नहीं है ना यहाँ पे तो फिर इट डजेंट मैटर कि आपने x1 पिक करना है या x1 बार पिक करना है. उससे कोई फ़र्क नहीं पड़ेगा. राइट. जब मैंने ब्लू एच ऐड कर दिए इट फोर्सेस मी टू थिंक मोर सिस्टमेटिकली बिकॉज इफ़ आई पिक x1 तो फिर ये वाला एच भी कवर होगा और ये वाला ब्लू एच भी कवर होगा. ओके. इफ़ आई फॉर एग्जाम्पल अगर ये एच कवर हो जाता है तो फिर देन 2 वर्सेस विल सफाइस टू कवर द रेस्ट ऑफ द ट्रायंगल, है ना. लेकिन अगर मैं यहाँ पे थोड़ी सी गलती कर जाता हूँ और x1 की बजाय x1 बार पिक कर लेता हूँ तो देन आई एम इन ट्रबल. राइट. देन आई वोंट बी एबल टू कवर दिस ब्लू एच. इस ब्लू एच को कवर करने के लिए मुझे ये वाली वर्टेक्स उठानी पड़ेगी और फिर x2 बार के लिए जो ब्लू एच है वो मुझे कवर करना पड़ेगा विद सम अदर वेरिएबल, है ना. सो ईच क्लॉज रिक्वायर्स कि उसके अंदर एक ट्रू लिटरल होना चाहिए. ओके. उसका जो ट्रू लिटरल है उसको मैं वर्टेक्स कवर में नहीं डाल रहा. उसके अलावा जो 2 वर्ड्स हैं उनको मैं वर्टेक्स कवर में डाल रहा हूँ. वो जो लिटरल ट्रू हुआ है दिस मस्ट बी कवर्ड बाय द वर्टेक्स जो ओरिजिनल आपके इंडिविजुअल एचेस हैं. ओके. ओके. क्या? सॉरी दोबारा बोलो.
अगर x1 ट्रू था तो हम उसको वर्टेक्स कवर में डाल दें.
अगर x1 ट्रू था हम उसको वर्टेक्स कवर में डाल दें. यस.
कि जो ट्रू है
हाँ. सो दो चीज़ें. सॉरी. सो within a clause you need to have a variable that is set to true. You need to have a literal set to true, है ना. Fix that. उसके अलावा जो remaining 2 वर्ड्स हैं वो आपने पिक करनी है अपने वर्ड्स के अंदर. ओके. सो इस clause के अंदर if x1 is the variable that makes this clause true you don't pick this clause, this node. Okay. इसके corresponding जो ऊपर वाले एज के अंदर वो वेरिएबल है नोड है वो आप पिक करते हैं अपने ग्राफ के अंदर. दैट्स व्हाट आई एम सेइंग. क्या? ऑलराइट. अनफॉर्चुनेटली दैट्स स्टिल हाफ ऑफ द प्रूफ. दैट शोज कि अगर आपका ओरिजिनल फार्मूला सेटिस्फाइबल है तो यू कैन फाइंड अ वर्टेक्स कवर ऑफ साइज n+2m, है ना. अब ये वाला काम है कि अगर ये वाला ग्राफ हैज़ अ वर्टेक्स कवर ऑफ साइज n+2m then I can find a satisfying assignment of my formula. That's not hard, but if you can help me with that. So this in the other direction that if I can find a vertex cover of size n+2m then I have to find out a way to satisfy this formula. Which variables should I set to true and which variable should I set to false? बोलो.
जो ट्रायंगल्स में हमने जो हमने वेक्टर्स में चूज किए थे
हाँ.
अगर उनका corresponding to h है तो
हाँ.
हम true करते हैं.
हाँ. Absolutely. So such reverse problem है कि जो भी मैंने वर्टेक्स कवर यहाँ पे पिक किया है उसके अंदर इस ट्राइंगल में जो 2 वर्टिसेस मैंने पिक की हैं उसके अपोजिट जो वर्टेक्स है उसके corresponding variable should be set to true. Okay. So if I pick this इस ट्राइंगल के अंदर x1 x2 बार और x3 को वर्टेक्स कवर के अंदर डाला है तो I need to pick x1 I need to set x1 to true. Okay. इस यहाँ पे I picked x3 bar and x5 so I need to set x4 to true. यहाँ पे I picked x3 and x6 so I need to set x5 to true. Okay. थोड़ा सा यहाँ पे एक टेक्निकल चीज़ है वो ये है कि you need to still show कि you will never have a vertex cover जिसके अंदर you picked all 3 vertices in a clause. Okay. अगर ये ग्राफ मैं आपको दे दूँ तो फिर यू आर अलाउड टू पिक एनी वर्ड्स दैट यू वांट, राइट? यू आर नॉट फोर्स्ड कि इसमें से 2 आपने पिक करनी है, इसमें से सिर्फ एक पिक करना है, ऐसा तो फोर्स नहीं कर सकते ना. So you show if this graph has a vertex cover of size n plus 2m, then they must have picked 2 vertices from each of the triangles and they must have picked 1 vertex from each of the individual edges. तो वो वाला पार्ट भी आपने करना है. But that's kind of I think one line intuitive proof. Yeah, go ahead.
I was going to say कि अगर हम किसी भी triangle में तीनों चुनते हैं then that would correspond to a literal वाला जिसमें हमने नहीं चुना to maintain the n plus 2.
हाँ, देखो वो वाला आर्गूमेंट यहाँ पे नहीं चलेगा क्योंकि मेरा एक फॉर एग्जांपल ब्लैक बॉक्स है जो वर्टेक्स कवर सॉल्व करता है. ओके, लेट्स से दिस इज़ अ ब्लैक बॉक्स वर्टेक्स कवर सॉल्वर. उसको आप ये ग्राफ देते हैं और वो स्पिट आउट करता है कि यस और नो. उसको इससे कोई गर्ज नहीं है कि दिस ग्राफ रिप्रेजेंट्स बुलियन फार्मूला. उसको नहीं पता कि ये वेरिएबल है या क्या चीज़ है, राइट? ये तो हमने डिज़ाइन किया ना. दिस इज अ ब्लैक बॉक्स, यू गिव इट अ ग्राफ एंड इट सेज or give it a graph and a number k and says कि there is a vertex cover of size k or not, right? So I think the argument is कि if you pick 3 vertices from any triangle, तो फिर आपके पास बाकी इतने नोड नहीं बचेंगे कि आप इन एजेस को कवर कर सकें, right? So if you pick 3 nodes from some of the triangles, first of all you must pick at least 2 from each triangle, right? वो रिक्वायरमेंट है, राइट? उसके बगैर गुजारा नहीं होगा. यू वॉन्ट बी एबल टू कवर द एजेस. 2 तो पिक करने ही करने हैं. बट इफ सम हाउ यू इंटेलिजेंटली डिड समथिंग एंड यू पिक 3 फ्रॉम अ ट्राइंगल, तो फिर यू हैव गॉन ओवर योर बजट, राइट? सो यू हैव इंस्टेड ऑफ 2m you used 2m plus 1, है ना? You used for example 3 here, 2 here and 2 here, which means कि you are left with n minus 1 to cover these edges. इन एजेस को आप n-1 से कवर नहीं कर सकते, राइट? बिकॉज देर आर n सेपरेट एजेस, you need n vertices there, right? So if you somehow pick 3 vertices from a triangle, you overused your budget, all right? And that kind of completes the proof. Let me quickly go through the slides in the next 2 minutes, okay? All right. Okay, so we saw this, right? This is how the construction works. This is how you connect the edges, connect the vertices in the triangle with the edges for variables. And here's the proof जो अभी हम discuss कर रहे थे, right? If there is a set assignment, then there is a vertex cover, and if there is a vertex cover of size k, then there is set assignment. Next हमने graph coloring करनी है, और हमने prove करना है कि graph coloring is also NP-complete. I'm going to share the slides for 3 coloring as well, so you can go through them before we meet on Wednesday. Go through them, come up with interesting questions or answers, I guess. We'll have our worksheet on Wednesday, start of the class, on flows. And maybe one more towards the end of the class too. Okay, let's see. Questions? All right, thank you. I'll see you on Wednesday.